Welcome to Lecture 18. Our first topic in this lecture will be decoders. And let's just look at an example to understand what we mean here. The first example will be it's something called a 3 to 8 line decoder, and we'll consider the three inputs to be A, B, and C, and our 8 outputs will be Y0, Y1, Y2, Y3, Y4, Y5, Y6, and Y7. And the way that the decoder works is that when ABC is equal to 0, 0, 0, actually, let me back up and say that for all 8 of these outputs, for any combination of the input variables, exactly one of the outputs will be equal to 1, and all the others will be equal to 0. So, when ABC is equal to 0, 0, 0, then Y0 will be 0. Y0 will be 1, and all the other outputs will be 0. When ABC is equal to 0, 0, 1, then Y1 will be 1, and all the others will be 0. For 0, 1, 0, Y2 will be 1, and all the others will be 0. So it's basically just decoding the binary number that we put in, and remember, we're considering that number to be in the order A, B, C, and then and that binary number will choose which of the outputs will be equal to 1, and everything else will be equal to 0. Well, in view of that, we can see very easily that we can come up with expressions for each one of these outputs as a function of the 3 inputs. We know that each output is equal to 1 for only one possible combination of the inputs, and that sounds like, and in fact is, a minterm. And therefore, all we have to do here is to identify which minterm corresponds to each output. Well, since Y0 is equal to 1 when A is equal to 0 and B is equal to 0 and C is equal to 0, the correct expression for that is A prime, B prime, C prime. When Y1 is equal to 1 when A and B are both 0 but C is equal to 1. So this should be A prime, B prime, C. Now I hope you can go ahead and fill out the rest of the options very quickly. I would suggest you stop the video for just a moment to do that, and then check your work. So the next one after that will be A prime, B, C prime, and then A prime, B, C, and then A, B prime, C prime, A, B prime, C, A, B, C prime, and finally A, B, C. So the decoder can be thought of as a minterm, or at least this decoder can be thought of as a minterm generator. Now, we can also invert these outputs, that would look like the following. So actually, let me go ahead and identify. So this is little m0, little m1, little m2, little m3, little m4, little m5, little m6, and little m7, just to emphasize that this is a min-term generator. But another thing that we could do is the following. Sorry. If we invert each of the outputs, so we have A, B, and C as before, and a 3 to 8 line decoder. And now, since we've inverted each of the outputs, this will be the M0 prime, M1 prime, M2 prime, M3 prime, M4 prime, M5 prime, M6 prime, and M7 prime. So in other words, we get the complement of each of the min-terms. But as we learned several weeks ago, the complement of little m0 is the max term, capital M0, and likewise the complement of little m1 of the min-term m1 is the max term m1, and so on. So the message here is that by inverting each of the outputs of the decoder, we can convert it into a max term generator. And so now I'd like to consider a couple of problems to demonstrate how the decoder could be used. So for instance, let's suppose that we were told or we were challenged with the following. Let's say using OR gates and or NOR gates and 3 to 8 line decoders with uninverted output, in other words, we're talking here about the first type of decoder, which is a min-term generator rather than max-term generator. So using OR gates and or NOR gates and 3 to 8 line decoders with uninverted output, realize the following pairs of functions and well, let's say choose the gates so as to minimize the total number of input terminals. And by the way, I want to give credit for this problem. This is from a book called Digital Principles and Design. Let's see if I can find here the edition number. This is the 2003 edition of that book, Digital Principles and Design, by Donald D. Givone, Givone. This book was used in the past in this course, 235, and I think it's a good book, and if you look in the library, you might find a copy there. But anyway, so this is one of the problems, and in part A, the pair of functions that we are asked to realize is f1 of x2 actually we'll keep it, since your problem has A, B, and C, we'll say A, B, and C is equal to the sum of the minterms 1 and 3, and f2 of A, B, C is equal to the sum of the minterms 3, 6, and 7. And this is a very simple problem to do. Let's draw our 3 to 8 line decoder. And by the way, I should say here, A, you're not allowed in these problems to use more than one decoder. So, for each problem. So let me make that correction. And so we have our 8 output lines here. And we can go ahead and label them, since this is the type of decoder that has uninverted outputs. We know that this is a minterm generator, so we have M0, M1, M2, M3, M4, M5, M6, and M7, and then our 3 inputs are A, B, and C. And we want F1 to be the sum of the two minterms 1 and 3, and F2 to be the sum of the 3 minterms 3, 6, and 7. And we're allowed to use OR gates and or NOR gates, and we're asked to choose these gates so as to minimize the total number of input terminals. And so this is extremely easy. We'll have F1 will be like this. Here's an OR gate. and that will give us F1. And then for F2, we want, once again, M3, M6, and M7. And there would be F2. And that's the answer to this problem. So it's a very simple problem. Now the next one, same instructions, but just a couple of different functions, and it's just a little trickier. Okay, we have F1 of ABC in this case. Is equal to the sum of the minterms 0, 1, 5, 6, 7 and F2 of ABC is equal to the sum of the minterms 1, 2, 3, 6, 7. Once again, we are allowed to use one decoder. Now, let's label these just as we did before. And let's start with F1. Now, if you're just working on this blindly, you say, well, this is just simple. This is very straightforward. It's just like our previous problem. We'll just take M0 and M1 and M5 and M6 and M7, and we will OR all of those together in order to get F1. But that will require an OR gate with 5 inputs. And remember that our instructions were to use either OR gates or NOR gates, and to here you can see this this second sentence in the directions. It says choose the gates so as to minimize the total number of input terminals. So I claim that what we should do here for F1 is, rather than ORing together 0, 1, 5, 6, and 7, we should NOR together the minterms 2, 3, and 4. So, in other words, I'm claiming that if we do this, if we NOR those 3 together, we will get the desired function for F1. Now, clearly, if that claim is true, that gives us the desired function, then that's better than our previous option of having a 5 input OR gate, because remember, again, we're supposed to minimize the total number of inputs, and this NOR gate just has 3 inputs. So this is preferable if it is correct, but the question is whether or not this is correct. So let's think about that for a moment. Okay, if you let's come down here and think. Okay, F1 is equal to the NOR of, now I'm saying this F1 that I've pictured, this is equal to the NOR of M2 and M3 and M4. Now we know from De Morgan's theorem that the complement of a sum is equal to the product of the individual complements. Oh, excuse me, I'm sorry, I've been started to use notation from another book. We're not using, some books use an overhead bar to denote complements, but in this course we're using a prime. So I should say then that F1 is equal to little m2 ORed with little m3 ORed with little m4 and then complemented. And again, as I was saying, De Morgan's theorem says that the complement of a sum is the product of the individual complements. So we have M2 prime, M3 prime, M4 prime. One last time, the complement, here the complement of a sum is the product of the individual complements. Okay? And now, as we said just a moment ago, the complement of a minterm is the corresponding max term, so this is capital M2, capital M3, capital M4. And notice that this is a product of sums expression for F1. And what this tells us is that if we write the truth table for F1, it will have a 0 in the 0, 1, 0, 0, 1, 1, and 1, 0, 0 alternatives for the inputs, and a 1 everywhere else. So in other words, what we have just verified, in other words, I'm going to say this is the same as this, but that is the same as this. Which is in fact the F1 that we want up here in part A. This matches this. So what we've done here is we have verified that the F1 that we have here in our picture, the F1 that we get as a result of NORing together the minterms M2, M3, and M4, is indeed the correct F1. It is the same as the sum of the minterms 0, 1, 5, 6, and 7. And once again, this is preferable, this way of getting F1 is preferable given the conditions of this problem. It is preferable to the direct alternative of using a 5 input OR gate to OR together the minterms 0, 1, 5, 6, and 7, because this requires only a 3 input NOR gate. And of course, you can imagine then what you should do for F2. Take a moment to think about that, and I would suggest you stop the video for just a moment, think about that, and then see what you come up with for F2. Okay, so I hope that you had a moment to think about F2, and we'll conclude that F2 can be thought of as the NOR of little m0, little m4, and little m5. That's we want to NOR those together. And by the way, I believe, let's see, in the previous, okay, no. Okay, so I've been consistent with my notation now. Okay, so we want to NOR those together. And so a way to do that would be maybe just have something like this. Here's M0. And here's M4. And M5. And again, we'll want to use a NOR gate to get F2. And again, we're trading off here. We're using a 3 input NOR gate rather than a 5-input OR gate that we would otherwise need to OR together these 5 minterms. Okay? And so now one final example. And this one I won't actually complete. I'll just give it to you to think about. So in this final example, we have F1 of ABC is equal to the sum of the minterms 0, 2, and 4, and F2 of ABC is the sum of the minterms 1, 2, 4, 5, 7. And so rather than drawing everything here, I'll just let you think about it for a moment. What kind of gate do you think you should use? Do you think you should use an OR gate or a NOR gate for each of these functions? Think about it for a moment and then turn the video back on and you can see. Okay, I hope that you have concluded here that for the function F1, which is M0 ORed with M2 ORed with M4, that you should use a 3-input OR gate. But for the second function, rather than ORing together these 5 minterms, what you should do is regard this as M0 or M3 or M6 and then complement it. So here, for this one, we would want a 3-input NOR gate. So that would be the way that you would realize that pair of functions. Now that we've seen how to do that, I would like to challenge you with another problem here. And I'll say, now, using AND gates and or NAND gates and a 3 to 8 line decoder with inverted outputs, generate generate the same pairs of functions. Again, choose the gates so as to minimize the number of inputs, the total number of inputs. So we're going to do exactly the same 3 problems, exactly the same 3 pairs of functions that we want to generate, but now rather than using OR gates and NOR gates, we must use AND gates and NAND gates, and furthermore we must also use a decoder that has inverted output. So in other words, we want one of the decoders that is a max term generator rather than a min term generator. So let's think about this. Okay, Well, if you will recall, in part A, we had the sum of the minterms 1 and 3, and the sum of the minterms 3, 6, and 7. So let's write that down. F1 of A, B, C is the sum of the minterms 1 and 3, and F2 of A, B, C is the sum of the minterms 3, 6, and 7. Now, my advice to you, since we're using a decoder now that will be a max term generator rather than a min-term generator, is to go ahead and immediately write both of these functions in terms of max terms rather than in terms of min terms. So if we do that, then this first function is the product of the max terms 0, 2, 4, 5, 6, and 7. And the second function is the product of the max terms 0, 1, 2, 4, and 5. Now we draw our decoder with inverted outputs. And recall that since we have inverted the outputs, now the outputs will be capital M0, capital M1, capital M2, 3, and so on. And go ahead and say 3 to 8, 9 decoder. And now we're ready to do this problem. And I hope that you immediately have a hint as to how to proceed. When we look at the first function, which is the product of these 6 max terms, we realize that if we're going to try to generate this function using an AND gate, then we will need a 6-input AND gate. We'll have these 6 inputs. And so immediately we think, well, isn't there an easier way? And the answer is yes. If we instead will simply NAND together max term 1 and max term 3, we will get the correct function. Now once again, just as we did above, I want to prove to you that that's correct. So we'll have F1 is equal to M1 ANDed with M3 and then complemented. And again, if we use the other De Morgan's law now that says that the complement of a product is the sum of the individual complements, then we have little m1, excuse me, getting ahead of myself here. So we have capital M1 prime ORed with capital M3 prime, which is indeed little m1 ORed with little m3, which is the sum of the minterms 1 and 3, and sure enough, as you can see right here, this is indeed the correct function. So this is correct. And likewise, you can imagine then that what we want to do with this second function is to, instead of ANDing together the max terms 0, 1, 2, 4, and 5, we want to NAND together the max terms capital M3, capital M6, and capital M7. So 3, 6, and 7. And that would be the way that you would complete that problem. And I believe that you can see how each of the other, we have two more problems we could do, the two other problems we did above, but I think having seen one, you now will see how to do the rest. So we'll conclude by saying that in this kind of a problem, what you should do is first of all ask yourself, what kind of decoder am I using? If you're using a decoder that is a min-term generator, then my strong suggestion to you would be to write your function that you want to generate in terms of min-terms. In other words, get the min-term expansion for it. On the other hand, if you want to if you have to use a decoder that is a max-term generator, then it's better to write your function in terms of max terms. And then once you've written your function in the appropriate way, I believe it will be easy for you to determine whether you should use OR gates or NOR gates in the case of the first kind, when you're using a decoder that is a min-term generator, and whether you should use AND gates or NAND gates in the case of a decoder that is a max-term generator. And of course, if you had a function that was a sum of 4 min-terms, it wouldn't matter whether you OR'd together those 4 min-terms or NOR'd together the other 4 min-terms, because in both cases you would get 4 inputs. And the same kind of situation goes for the case where you're using a max-term generator. So I believe that this kind of problem, I hope that this kind of problem is straightforward and easy for you, and it's a good example of the use of decoders. And by the way, an encoder just acts in the inverse fashion to a decoder. So that's it for decoders. And now let's look at some problems for this lecture. So now for the problems for lecture 18. All 3 problems will deal with this circuit shown here. And notice that our inputs are A, B, and C. We have a 3 to 8 line decoder. We have uninverted outputs. So this is a min-term generator, as is noted right here. And F1 is this is an OR gate. And F1 is the output of that OR gate. And this is a NOR gate, and F2 is the output of that NOR gate. And you see the connections here. And so 18.1 asks, what is the max term expansion of F1? And 18.2 asks, what is the min-term expansion of F2? And you see your choices in each case. And then 18.3, that problem will be given in class. So I hope you'll find that pretty straightforward. And that concludes lecture 18. So good luck.